Hello, everyone, and let's get started. We're going to talk about the second topic for Module 2-1 or Unit 2-1, which is on strings encoding and decoding. And this is a continuation of something that was an option in Lab 1-3, not required, but a possibility. And for those of you that did it this way, this lecture might help to clarify some of those details. And you may have even looked ahead in the lecture notes in the handbook and seen that we were talking about it here. So let's go ahead and get started. All right, so in this topic, what we're going to talk about is working with strings. And actually, chapter 5 in the Zell textbook is huge and contains a lot of material, a lot of foundational material for the class, and not just about strings. We're going to talk about working with data files. That's also in chapter 5. But strings are a core part of what Python is really, really good at. And I've mentioned that before. Strings and sequences. A string is a sequence of characters. But other types of sequences we've talked about so far this semester have been lists. And in the last lecture, I mentioned one called a tuple. But in any case, strings are what we're going to focus on today. We're going to talk about encoding and decoding the characters that are in a string and how we can work with those. So we'll just chat about that. We'll talk about parsing and processing strings as well, which is something that you've started doing in earlier labs, but we're going to keep doing that. And not just parsing and processing strings, but also parsing and processing lists and tuples and sets. And later on this semester, we'll talk about dictionaries. There's so many different types of sequences to work with in Python, but we'll get started here and talk about strings. All right. So did you know that you can do math with text strings? Some of you have done this. You've created a string, let's say a single equal sign in quotes, right? And you multiply it times 10 and you get a string that has 10 equal signs. Or you multiply it times n, where n is the length of some string. And you may have done that in milestone 1, where you've got your title at the top and it has n number of characters and you want to put n number of equal signs below it. But we can do math with strings. We can do more than that. We can convert those characters to a number, an integer, and then do math with them there. Something that's been used now for I don't know how many thousands of years is encrypting of messages, right? We might do substitutions where instead of the letter A, we'll use the letter X. Instead of the letter B, we'll use a dash, and so on, and encrypt a message. But we can mathematically encrypt messages by converting the characters to a number and then performing a math operation on them, some sort of algorithm. Maybe we add or subtract values, or maybe we multiply times 2 and divide by 3, and whatever integer is the result. That's the substitution character. So that kind of thing can only be done if we can convert a character to a number. And here's something that's important to know. Computers and Python do not store characters as a character. If you enter in the letters A, B, and C and you save those in a string, the computer does not save A, B, C. It actually saves 3 integers that represent A, B, and C. And because you've saved them as a string data type, it knows to convert them to the characters corresponding to those numbers. Every character corresponds to a unique number. So here's something I'd like you to do. Pause the video, open your handbook, and go to the very last page and take a minute and look at what's on that page. It's called an ASCII table. Go ahead and do that now. Pause the video, grab your handbook, go to the last page, take a look at it. I'll wait. All right, hopefully you've done that. You've paused the video, you went and looked. That table is the conversion table that computers use to substitute an integer value for a character. And you notice it's not just alphabetic characters, A through Z, lowercase and uppercase. It's also all of the punctuation marks and hyphens and quotes and left and right parentheses. It's also a lot of non-printing characters like tabs and spaces and new line characters like pressing enter on the keyboard. And there's a bunch. There's even one called bell, which on some computers, when you print the bell character, it goes ding. I don't know. Anyway, so there's a lot of different characters out there in the ASCII table, and they can all be displayed on your computer screen. Well, those that actually have a display. Some of them do something like tab, for example. So we can do math with strings by breaking them down into their unique characters and then converting those characters to a number. Let's do a quick little review of for loops, something that many students have mentioned they struggle with is for loops. And one of the reasons why I think a lot of students struggle with for loops is that they're not understanding them on a fundamental level. A for loop steps through a sequence of values, substituting them for a variable. Check this example. I've got a string called myString, and it equals boiler up, right? And actually it equals capital B, lowercase o, I, L, E, R, capital U, lowercase p. To a computer, that doesn't say boiler up, it's just a sequence of characters, right? So myString is this sequence of characters. For each character in myString, this for loop is going to look at one character at a time inside the for loop. So anytime I use this variable character inside the for loop, it'll just be one of these characters at a time. So the first time for character in myString, this is myString, the first time character is given capital B, and it says print that character. The loop repeats. What is character given the second time? The lowercase o. So it prints a lowercase o. This is the output. Each character printed individually on a line by itself, because the print function accepts the value, prints it, and then it presses enter, or a new line at the end. It does it automatically. That's why it's B, new line, O, new line, I, new line, L, etc. You get that. The for loop is going to step through or look at each value in the sequence. And if the sequence is a string, then it's going to look at each character in the string. If the sequence is the result from a range function gives you a series of integers with a starting and an ending point. If the sequence is the values in a list, then it's each entry in the list. All right, so string sequences can also be accessed using their index position. We talked about this before, but let's do a quick little review. If myString equals boiler up, then myString index position 0 is the capital B. And index position 3, remember this starts at 0, so 0, 1, 2, 3 is the lowercase l. And myString, the slice, starting at 0, going up to but not including 3, 0, 1, and 2 is boy. myString starting at 6, going to, what does this mean? Well, if you'll recall from slicing and strings, when we don't specify a value, it means to the end. So starting at index position 6 and going to the end, this is index position 0, 1, 2, 3, 4, 5, 6 is the capital U. Going to the end, we're going to get up. Right. So the index position is the order of the characters in the sequence. In this case, the string is our sequence. The first position is always 0, don't forget, and we can use slicing to pull out bits and pieces of the string. In this case, I grabbed index position 0, 1, and 2. In this case, I grabbed index position 6 to the end. So we can use slicing to do that. The \n is the new line. It's like pressing the enter key on the keyboard. So if I say print, inside my print statement, I put in quotes, hello, \n world, it's not going to print a backslash or an n. It sees these two characters together as meaning press the enter key. So hello, and actually this has got a typo in it because that should be a lowercase h, right? I didn't tell it to print an uppercase h. Let's just fix that. Here we go. It prints hello, lowercase, then a new line, and then world in lowercase. The new line character is here, \n. The \t character is a tab. Tab on your keyboard means 4 spaces primarily. So if I say print hello \t world, it's hello 1, 2, 3, 4 world. So it puts the tab character between them. And you can use \t as a tab character. There are a lot of special characters, and you'll find them all in the ASCII table at the end of your handbook, and you can use them for, to a certain extent, manipulating and controlling the appearance of text. A shortened version of the ASCII table looks like this. This is not the whole table, but there's a bunch of it here. So the space key on the keyboard is ASCII value of 32, exclamation point is 33. I don't need to go through all of these, but here's all your punctuation marks and other elements for math and braces. And then you've got The uppercase characters, capital A through Z, which are ASCII values 65 to 90. Conveniently, they're in numeric order. And notice this only goes up to 90, skipping up to 97, so there must be some values between those, is lowercase a through lowercase z. There are 256 values in the ASCII table. So we have a lot of possibilities. Now, that does not allow us to display every single character that is used on the planets. Like, for example, where do emoticons come from? Where do emojis come from? And those are their own characters. Well, there's a much larger table where the first 256 values are identical to ASCII values, and then another 65,300 and more are above that, and that table is mostly empty, but right now it contains all of the printable characters in the world's languages, and emojis, as they are created, are assigned positions in that table, and that table is called the Unicode table. We don't have access to the Unicode table directly in Python. You can, but by default, we have access to the ASCII table, the first 256 characters that are printable or displayable or that you can work with on the screen. Right, so we can convert values back and forth from the character to its ASCII value, numeric value, and then back from the numeric value back to a character again. And this is done using two commands, the ORD function and the CHR function. If I do ORD and a character, for example, lowercase b, it's going to tell me that that is has a value of 98. Coming back to my table here, 98. 98, 98, here it is, 98, lowercase b, there it is. And if I say, what is the character at the ordinal value of 98, it's going to tell me it's lowercase b. So I can convert back and forth using the ORD and the CHR commands to convert them back and forth. So if I want to encode my message, I might look at each character one at a time and then get the ordinal value and then maybe do some sort of math operation to that, and then get the character that matches it, right? So I start with 98, maybe I increase its value by 5 or something, offset it by 5, and then I get the character value for that offset. It would be something that's not B anymore, but 5 after B, right? Which would be G. So B, A, B, C, D, E, F, G would be G, wouldn't it? So I convert it to another character as a substitute, and that would be a way to encrypt my data. All right, so let's take a think. Let's think about this. What if we were to prompt the user for a name and sum the ASCII values of their characters? Now, we did something similar in Lab 1-2, except we did not sum the ASCII values of the characters. We said A is equivalent to 1 through Z being equivalent to 26, all lowercase. Sum up those values. So this is similar, except we don't want to convert A to 1 and B to 2 and so on. We want the true ASCII values and sum those up. So my name is Gary, capital G, A-R, and then lowercase A-R-Y. Looking at the ASCII table, capital G is 71. So my program would take my name, G-A-R-Y, would look at capital G, get 71, would look at lowercase a, get 97, add those two together. What does that come out to? That's 98 plus 70, which would be what, 168? Yeah, 168. Then R, lowercase r, 114. So 168 plus 114. I'm trying to do math in my head. It's 200 and I don't know, 70 something, right? And 280 something. And continue with Y, adding 121 from Y to come up with that values. But I don't want to do it just once. I want to be able to do it with any name. So I'll prompt the user for a name and then sum up the ASCII values of the characters and then display that result. How about I prompt the user for a sentence and I calculate the average number of lowercase letters per word? Well, how do I know if they're a lowercase letter? Well, I could look at their ASCII value, right? Or what if I created a sequence of characters that are all the lowercase characters and calculated those up? Basically, what I want to know is how many words are in the sentence, how many lowercase letters are in each of those words, and then divide that by the number of words, and I know how the average number of lowercase letters per word are, right? So, but you've got to be able to look at whether they're lowercase or not, and you've got to be able to do some programming to figure that out. So, as a summary, a string is a sequence, and we can use that sequence in our loops, our for loops specifically, but in any sort of sequence. And we can manipulate the individual characters in a string and even convert those characters to numeric values and back to characters again. And that is the magic of how we do encoding and decoding. You're going to be doing some of this in your labs this week. Come back, review this, look at the notes in your handbook. There's some examples there. Don't forget to take the quiz that goes along with this lecture. And I will see you next week. Have a great week.